All right, I'm on the PowerPoint from Chapter 18B. I'm on slide number 4. And this particular this particular slide goes over the common ion effect. So it's asking, is it possible to dissolve more silver chloride in pure or salt water? So let's write the dissociation for silver chloride like this. Of course, these are aqueous. And we'll imagine two different scenarios. In the first scenario, we don't have to worry about solid, of course. Of course, if we're in pure water, then we can start out by assuming that there's no silver present and there's no chloride present, and we're going to get X amount of each. And so our KSP would be equal to the concentration of silver at equilibrium times the concentration of chloride at equilibrium. Those are both X. And so KSP, which for this particular salt is 1.8 times 10 to the negative 10, that's going to be X squared. And if we take the square root of 1.8 times 10 to the negative 10, take square root of that, we get 1.34 times 10 to the negative 5th molar for both. Now, so we found out how much silver chloride we can dissolve in pure water. Now we're going to look at salt water. So in this case, we'll start with silver chloride solid dissociating again into silver ion and chloride ion. There's going to be some initial conditions, a change to get us to equilibrium. We're not going to worry about the solid, of course. In this case, if we're in salt water, there's going to be some dissociated chloride ions, right? Salt, sodium chloride. If that goes into water, you get sodium ions and you get chloride ions. So let's just say we have, 0.1 molar, kind of salty water, chloride ion in the water. We don't have any silver. What's going to happen in this case? Well, we're going to gain X amount of silver. We're going to gain X amount of chloride. And so at equilibrium, we're going to have X amount of silver, 0.1 plus X amount of chloride. And once again, we know that KSP, which is 1.8 times 10 to the negative 10, that's going to be equal to X times 0.1 plus X. Now we could solve this directly in a way where we're going to have to, if we do the full algebra, we're going to end up having to solve a second order polynomial. But we probably recognize, even in pure water, that the amount of dissociation is going to be really tiny. 1.34 times 10 negative 5th, if that's roughly the value of X, that's really small compared to 0.1. So we're going to assume this is 0. So we're going to say X is going to be less than 5% of 0.1. Let's see what that is. 0.1 times 0.05. You all remember this particular approximation we make. So it's got to be less than 0.005. We need to come back and check that. But wow, if I do that, look how easy this becomes. KSP, which is 1.8 times 10 to the negative 10, that's going to be equal to 0.1 times X. We divide both sides by 0.1. And if you do the math, you'll find that in this case, X is 1.8 times 10 to the negative 9 molar, which is certainly less than 0.05. This assumption's justified. All of this to get us to help you understand what the common ion effect is in relationship to the dissolving of salts. In the case where we dissolve silver chloride in pure water, we found a concentration of 1.8 times 10 to the negative 5 molar. That's how much silver ion and chloride ion we could get dissolved into the solution. So let's look at this as, this is going to be the concentration of silver, of course. 1.34 times 10 to the negative 5th. Here, X, which is the concentration of silver. Holy cow, what's that? 10 times, that's roughly 10,000 times, 10 to the 4th. That's roughly 10,000 times less concentrated silver. And the idea here is that when an ion is present that's common to the salt, when it's already dissolved in the fluid that you're trying to dissolve the salt in, a very little amount of that salt can dissolve relative to how much of that salt can dissolve in pure water. That's the common ion effect. So let's use the common ion effect to answer this question. Is it possible to dissolve more calcium hydroxide in an acid or base? Calcium hydroxide in acid or base. Well, let's think about this. So I've got calcium hydroxide, which is an insoluble salt, but a little bit of it will dissolve in water. That's 2 of those. We're not going to worry about this. What we see is in pure water, we're not going to have any calcium present initially and any hydroxide present initially. And so quite a bit will dissolve, but if we're in a base, we're going to have quite a bit of hydroxide present. And if there's quite a bit of hydroxide present, we'll say 0.1 molar, we're going to see the same kind of thing happen last time, where not as much as this is going to be dissolved. So we would guess that calcium hydroxide will be less soluble in a base than an acid. And we can also use the principle of Le Chatelier to predict this as well. I mean, if I increase the concentration of hydroxide, that's certainly going to shift this equilibrium in this particular direction, which is away from solubility and towards the solid. Both of these questions exemplify the idea that's important in the common ion effect.